Hello, hello, hello. Can I get a, oh, hello, Euban, good to see you. Um, hello, Sarah, good to see you. Hello, can I get a hello from anybody or could I see if, can you hear? Good to, thank you, thank you. Okay, I'm gonna take it that that means that he heard me, that's good. Thank you, and all right. So hello, Euban, hello, Sarah, hello, the person who's coming in right now, and now I'm doing the, hello, Steve, good afternoon, Steven, good afternoon, Brianna, good afternoon, Katya, good after, okay. You guys are welcome to say hello to me. It wouldn't insult me. I'm just saying. Good afternoon, Samaya. Good afternoon, Katya. Oh, yes. Good afternoon, Katya. Oh, and Abdel Rahman. Good afternoon. Or did I say that? No, I didn't. Here comes KK. Okay. Top of the afternoon. I love that. Top of the afternoon to you, Abdel Rahman. Good. Hola, ¿qué tal, Brian? Hi, Kay. Awesome, awesome. All right, now we're talking here. Or now we're, oh, and I said, oh, and hello, I was just about to say hello, Jasmine, and then she like literally appeared. She like materialized. That's awesome. Hello, Jasmine. All right, that's awesome. That's 1,000,000 points. Don't forget to submit. Hello, excellent. Oh, 1,000,003 points. Okay, so we have Jasmine, we have Kay, we have Brian, we have Abdel, we have Katya, we have Sumaya, we have Anna, we have Stephen, we have Euban. Did I say Sarah? I feel like I'm saying, not, I feel like I should say Sarah more for, oh, I know why, because I'm seeing her, but I'm not chatting her, right? So hello, Sarah, right, okay, and now, whoa, wait, okay. Oh, good afternoon, thank you, awesome, okay, and it wasn't a thing, it was a thing. Okay, excellent. Thank you. Can you imagine? It's probably just as well that you guys only know me electronically and two-dimensionally. I don't think we could even handle it. If you, have I seen any of you in the halls? No, but I don't think, but okay. But I will, by gosh. Oh, good afternoon, Jose. Thank you for saying so. Good afternoon. All right, so we have a quorum, so to speak. Oh, okay, wait, I'm looking at the chat. Oh, okay. Okay, thank you very much, direct chat person. Got you. I see you, I hear you, I appreciate it. Totally understood. Thank you for the communication. I will stop talking now, but yes, I got you, direct chat person. And there's only one, so if you chat to me, then you know who you are. Okay, or did that just like ruin the whole point? I'm not sure. Okay. Okay. So again, we're gonna start. Oh, okay, good. Okay. You know what? No, all right, I'm gonna go. I'm so right. I have no what's that word? Filter. Right. No, the saddest thing is, you want to know the saddest thing, people? I'm gonna tell you right now, but we're gonna do physics. Okay, wait, just to force me to do physics, we're gonna do physics. Okay, that's a good boom, boom. Okay, that will help force me into the physics. That's what's all okay. Digression number 2. What's sad is like physics is my favorite thing, and even that I can't stay on the subject. Like that makes no sense. But and number 2B is I already forgot what I was just gonna say. No filter. Oh, the saddest thing is, it would seem that I have no filter. It just seems like I just think out loud and just say whatever's coming to my mind. It's sort of true. But what's really sad is I actually do have a filter. Can you imagine what I'm not saying? That's like truly scary. Okay. All right. But we're going to start. Hello. Just like a couple quick announcements. Okay. Maybe we actually have a full week of physics this week. That would be nice. I actually think we are making tracks. That's the craziest thing. I think you're good afternoon. All smile. Good to see you. And oh yes, I mentioned already. Yes, I've actually seen her live and in person. In case you didn't know, All Smile actually has 3 dimensions. So does Sarah, I think, but meaning that they actually exist as real people. Yes, you do. That's so great. Your parents must be so proud. We're actually making tracks in this class. That is to say, of all the homework that's been assigned, we've actually gone over just about all of the questions. There's like one more question on the very last homework assignment that I'm going to say some things about today, but then we're going to move on. Now, speaking of homework, a couple of things. Still the homework is coming back in strange orders. It's coming back like, hopefully some of you got even more things back this morning. The order makes no sense. Some of you are getting back things that you did more recently and you're still missing things. You're not missing, but you're still like waiting to get things back from earlier. I totally know that. Again, for some reason, it's just turned out to be more efficient for me to go turn them back in the order that the notifications appear on my device. Like, that's completely stupid, but that's what's, so you're getting things in like, and whatever, it's just all catching up and it's continually happening. Hopefully you're seeing every now and then something comes back. As far as the actual answers and how to do the work, that's what we're doing in class, and that we are caught up with ourselves, which is good. Therefore, one new homework was posted. So many of you have gotten, I believe, I get the two classes confused, but I believe even though some of you still haven't gotten back like number 2 or something, many of you have gotten back number 4. Again, that is, just know that if you haven't gotten it back, it's on me, not you. I know I say this every time, but I just want you to know that. But it also means, like I say every time, if there's anything that you haven't done yet, you still absolutely can and should. And there's no penalties for lateness, like hopefully not to me, but also not to you. Just do whatever the next thing is that you haven't done yet. So a new assignment got posted today. That's due a week from today. There's no new equations in this new assignment. There's no new knowledge. Now, it's kind of like the last assignment on this material. It's practice and application of this material that we're doing right now, which is technically the constant acceleration material. But just a quick warning or a quick heads up, the new assignment, you have a week to do it. It looks bigger than all the prior assignments. It is. I mean, it's more pages. There's more problems. It is worth more points when you do it. Even if you don't do it by next Monday, just whenever you do it, you can get more points. It has some things that are practice. I mean, it looks long. It is long. It'll take some time, but some of the problems are just practice exercises, whatever. Some of them are not. The assignment is called Big Old Duck, and all the problems build to the very final problem. If you had to just do one problem from the whole thing, or you had to triage, or you were trying to like know what the most important thing is on it. The most important ultimate thing is the very last problem. Sort of everything is preparation for that. So that very last problem, Big Old Duck, again, it doesn't have new knowledge in it. In principle, you could do it right now with the equations and the knowledge that we have thus far in this class. In principle, you could, but it is hard. You do have to think. It takes a number of steps to do. It will use knowledge from lab 3 and lab 4, that even though you don't have to have done those in order to do it, but it also maybe help you understand some things that are going on in lab 3 and lab 4. We're going to talk we're actually going to talk a lot today about lab 3. I'm going to try to make some of it. I know you already did it. Actually, let me ask. I know you did it, but do you still have anything? Did you already turn in lab 3, or do you still have anything? You could tell me in the chat. I just don't remember. Did you already turn in anything that was due for lab 3, or are there yes, you do. Oh, yes, we do. Are there any? What is due next in lab? I guess that's my question. If you don't mind answering in chat or with voice or something. I'm looking at, like, what is something due in lab? Oh, putting everyone on the spot here. Well, and she's like, see the people, again, you don't have to show video, but I'm just saying the people that do show video are like sending so much human information to me just by, like, they really do make it okay, I don't want to, but it like really, those of you, Sarah, who are showing video, it's like, it really helps a lot. It really does. It's just, oh, okay. Cool. Thank you, Jasmine. Totally appreciate. Oh, funny. It was a video person. So, oh, did I say that? Okay. So cool. So you're on lab 4 now. That's great. So everything we're going to be talking about today is very relevant to lab 3 and lab 4. But can you tell me, Jasmine, or anybody else, did you turn in, like, is something due have you already done reports on lab 3? I mean, if there is a report, did you already turn in or oh, lab 4 is due next week. Okay. Okay. Thank you, Kay. That's super helpful. Okay. So what I'm going to talk about today, it might help you write your reports when it's time for lab 4. It might be a little bit more, it's too late to help you write your reports for lab 3, but it may help make sense out of what you did in lab 3. If nothing else, it was, it's like everything else, like the calculus just feeds back and forth with the physics. Lab feeds back and forth with the lectures. Like it's chicken egg. Like sometimes lecture helps lab. Sometimes lab helps lecture. Sometimes you think of one first and the other second, but they are meant to be connected. They are definitely not meant to be just two random separated curricula. I assure you of that. So we're going to address a lot today are the concepts that are going on in mostly in lab 3, to some extent in lab 4. But the big problem at the end of the newest homework that was just posted, the big problem at the end, which is called Big Old Duck, that problem ties together stuff from lab 3 and lab 4. And also just to warn you, when we get there, we're not there yet, but generally the very last problem on the homework, Big Old Duck, is one that generally appears on an exam or like a version of it. Like it's an exam type problem. So this newest homework that I just assigned, if it looks long to you or looks big, it is kind of a preparatory packet for any exam that might happen. Like that's what it kind of, not that you won't still get one, you'll still get a more direct review document. Hi, good to see you. Awesome. Awesome. Thank you. But the most recent homework is probably the most, is a very good review document, put it that way. It doesn't mean it's easy, but it's a comprehensive review document. And the last bit of it absolutely is what like part of the exam looks like. Okay. Last thing I just want to say also with the game turns in the games, which I think people are understanding. I think the homework that I'm doing the homework in fits and starts, but the homework that I'm seeing is impressive. I forget if it was this section or the other section, but a lot of you ultimately did that 5-step method optional homework. Like you put some time into showing me that you know what the 5-step method is. And I think it really paid off for a lot of you, not just in the points that you got for that, but the homework that I'm seeing so far, honestly, is very impressive and very thorough. And it really does seem to me that you guys are getting the 5-step method. And I think it's helping you do the physics. So essentially, there hasn't been a bad grade on homework yet. Like anything I've gotten to or anything you've done, you can be pretty confident if you've done it at all. Once you get it back, it probably did get you a lot of points because I'm very happy with them so far on the whole. That said, with the game turns, same deal. Just know that all of those special game assignments, they're all optional. But any game, like a lot of you in the game turns will say something like today, I said hi in the chat and I showed video. And you'll even like screenshot, show me, which is great. And this is just an example. I'm not trying to praise the video people again, although I totally am, but it's just an example. Like say you write in the game turn, I said hi in the chat and I showed video. Here's a screenshot. That's totally awesome. And you'll get the 5 points. And I love you for doing it. And I love everybody in a completely professional way for doing it. But then if I write double dip, I'm saying to you, okay, please note that there's also a portal specifically for showing video or showing an avatar like Kay does, for example, or Katya does, or Ashley does. There's a separate portal whenever you show that you also can submit in there. It takes you another extra 2 minutes. But if you also submit that screenshot into the portal that says avatar or the one that says video, if you're showing video, that's like just more points that you get. And if you're the type of person that's showing an avatar every day or a video every day, you can keep submitting that. Like, it's not a joke. Like, I don't know if it seems weird or not, but like, you can get points every time if you just, keep re-uploading. So please know that all those special portals, if ever I say double dip, I'm saying there's another portal somewhere there, find it. And, it may say due December or something, but it means you can do it anytime. Therefore, or why I'm saying all this is a new version of that opened up today, like another portal opened up called Your Written Records or something. That's an option for people who have been totally engaged, totally paying attention, totally doing the work. And there are many of you, but like, don't make a lot of noise. That's completely fine. You don't have to make noise or sound. or show video in order to be like getting something out of this class. If you take really good notes, if you take if you take notes and you're at all proud of them and they look at all like your stuff, not just mine, take a screenshot of your notes, maybe particularly like a nice part, like with a picture that you made, a sketch or something, or when you used more than one color, or when you like annotated something in your words rather than mine. Just take a screenshot and submit that to the portal that says your written records. And that's points, just a way of saying like, I'm in this class, even though I don't love calling attention to myself, I'm totally doing stuff in this class. Okay, so please use that. It's all optional, but I'm just saying there's 1,000 different ways to try to get something out of this material, and there should be 1,000 different reward systems and incentives therefore. Okay, and if you think of another way in which people can be engaged, but that I haven't like specifically acknowledged yet, send me a text and tell me. I know I say this every time, but it happened today. A new portal went up today for people who take good notes, so use it. Okay. And stop me if there's any questions. But that all said, we're going to continue with the material now. What's on the board right here? I'm just changing the view. Sorry. What's on the board? See, people are even getting see, some people are getting comfortable, like on a couch. Okay, whatever. All right. Which is good. That's good. So on the board right now, there's two equations. It looks like three to some of you. There's two actual equation statements, and they're both preceded by the condition if and only if A equals A naught. That's the condition. That's the context that we're in right now in the material. That condition means constant acceleration, a value of acceleration that doesn't change from the beginning. It means velocity is changing, but the way in which it's changing is not changing, right? That's the context that we're talking about right now. Now, we already derived one equation for that. One equation that we already derived or set up for constant acceleration is V bar equals V naught plus V over 2. It's not written on the board here, but it was the first constant acceleration equation that we established like early last week. We talked about it for 2 classes. Hopefully it's in your list. That it was the last one in that cumulative list that we established last Wednesday. Then at the end of last class of last Wednesday, at the end, we established a new equation, the one that's written in the middle of the screen right here. Like x minus x naught equals 1 FA2 squared plus V naught T. We're going to be using that a lot. We did like one exercise or one problem to establish it in the last homework. It's the second example of a constant acceleration equation, right? It's the second example of an equation that is true whenever acceleration is constant, but it's only true when acceleration is constant, right? It's only true if you have a value for A that you could plug in there that's not changing. We're going to use it a lot more. We're going to practice it, but we established it at the end of last class. What that is that's like the distance equals rate times time type equivalent. The equivalent of saying distance equals rate times time when the rate that is given isn't just some constant or average velocity, but when in fact the rate that's known and given is a rate of acceleration. This is what you use. It's technically called the position function for constant acceleration. That's what we established last class. We're going to use it more and more, but it was established last class. But the equation below it is what I want to get to today. It's one of 2 things I want to get to today. It's the third constant acceleration equation. It's the last of all the equations we're doing in this topic. We haven't said it yet. We're going to say it today, but where it comes from, where it comes from in our context, is it comes from the very last problem, Roman numeral problem. I think it's Roman numeral 2. In the very last problem in homework 5, the one problem we haven't gotten to yet. I will share the screen when we get to it. The one problem that we haven't gotten to yet, where it looks like it's just asking like this raw algebra. It's just saying, show that if A, B minus C, D equals G, and it just seems like a weird out of nowhere algebra problem that's asked for you. You're asked so that you can make sure you understand the algebra that is required for where we get that equation. So I'm going to show you that today. That's the goal of today. So I'm assuming the top equation you have written at least once from last week. The bottom equation is what we're trying to get to today. Okay. Both of them have an A in them. Both of them assume some sort of unchanging value for acceleration. But I'm going to turn the page now. I'm going to say something before I finish that last problem from homework 5. And before I go on to do one of the problems for you of homework 6, that is by the end of today, I'm going to start the homework for you and knock off one of the problems for you as a reward for paying attention. Before I do those two things, before I finish homework 5 and go to homework 6, I want to talk about the most among the most naturally occurring, common, daily encountered, reliable examples of constant acceleration, right? And again, remember, constant acceleration means unchanging change. A constant acceleration is when something is changing its velocity, is changing the rate at which it moves through space per time, but it's not changing the way it changes velocity. That's like a mouthful, but that's what constant acceleration means. It means you're changing velocity, but you're not changing the rate at which you change velocity. Now that's like a weird, in other words, for the mathematicians in the room or the growing mathematicians in the room, constant acceleration means when there is a constant second derivative of position with respect to time. When position is changing, hence there's velocity, and velocity is changing, hence there's acceleration, but acceleration is not changing, hence there's no jerk. So when there's two derivatives of position with respect to time, but there's not 3 or 4 or 5, there's exactly two derivatives of position with respect to time is what we mean in physics terms by constant acceleration. That's what we're studying now. And that sounds like a very specific thing. Like, well, why are we focused so hard on derivative number? Why are we focused so hard, which we are, on derivative number 2? Like, why are we doing like a whole chapter on when derivative number 2 is constant? What, like, why not derivative number 3, or why not all the derivatives or whatever? And the answer is because there's a lot of circumstances in nature where this occurs, where there is a first derivative and a second derivative, but there is not a third derivative of position with respect to time. This is a naturally occurring, very standard, pervasive phenomenon. And the chief example of naturally occurring constant accelerations is free fall near the surface of the Earth. So we're going to turn the page and discuss that for a minute. And this is what Lab 3 is all about, and slightly more elaborately what Lab 4 is about. It's about free fall. So we're going to pause for a minute and address this notion of free fall. And let me say again, free fall is a specific example of constant acceleration. Free fall is a naturally occurring daily, like real life application of constant acceleration. So we have to say some things about it. In fact, physicists love free fall. I mean, a lot of physics centers on an investigation of free fall. So first of all, let me say the definition of free fall. What we mean when we say free fall, we have here free fall, triple equal sign, an object subjected to no external influence nor interaction other than that of gravity. For an object to be in free fall means it's not interacting with any other object, i.e., it's not touching any other object. It's not in contact with any other object. It's not being pushed or pulled, or as we say in physics, forced by any other object other than, apparently, planet Earth. If something's in free fall, it's being affected by nothing but planet Earth. And it's being affected, if it's in free fall, it's being affected by planet Earth, not because planet Earth is touching it, but because planet Earth evidently, apparently, has this ability to pull on things through empty space and pull objects at all times toward its center. Like now that's a mouthful right there, but that mouthful is what we call gravity. So in short, I'm saying for an object to be in free fall means for it to be subjected to no influence other than gravity. And when I say gravity, I don't mean to assume that you or I, or even Galileo, has some huge amount of mathematical understanding of gravity. We will eventually. I'm not assuming that we know exactly how gravity works or why gravity works or any of the mathematical intricacies. They are there to be known and we will know them eventually. But I'm saying right now, when I use the word gravity, I just mean what countless people meant throughout thousands and thousands of years of history until about the mid 18th century. All I mean by gravity right now is the apparent reality that Earth sucks objects down to it, toward its center. That just the observable fact that when you let something go, it falls down. That's all I mean by gravity right now, that things seem, that what goes up must come down, okay? So when an object is left alone and nothing else is happening to it, you're not pushing it, shoving it, supporting it, or even blowing it in the wind. Like once there's actual wind and stuff, that doesn't count as free fall anymore. Once there's significant air resistance, which is a thing like that exists that you know about, once something is subject to significant air resistance, it might be falling, but we don't call that free fall anymore. In other words, objects on parachutes, just so you know, objects on parachutes or on hang gliders or something, they could be falling, but they're not free falling. They're being influenced by gravity as well as by what we sometimes call air resistance, or we sometimes call fluid drag or something like that. Free fall means if you're just literally falling, if you're heavy enough and non-aerodynamic enough not to be affected by the air and you're just plummeting toward the center of the Earth, that's what we mean by free fall. And here's the thing. Now, here's the thing about free fall. It happens all the time, obviously. It's all around us. And it's a type of motion. Physics is all about motion through space and time. Free fall is not only a very common motion, but it has a special property. Evidently, when things free fall, when they fall freely, they're falling. So they certainly change their position. When things are free falling, they go from here to here. Or even when you throw them up, and then they start coming down. I should make that clear too, by the way. Even when you throw something up, on its way up, that if nothing else is touching it and no air is really doing anything significant, even on its way up, we call that free fall. And even when something's going to the side, as long as something is just released and is just subject only to gravity, that is called free fall. So an object doesn't have to be moving down in order for it to be free falling. What it has to be is accelerating down. Now, why do I say acceleration? When something is falling, okay, first of all, it's certainly changing its position. Like it starts here, and then it's here, and then it's here. So it's certainly changing its position in time. So when things fall, they certainly have velocity. By definition, when things fall, they certainly have velocity. But is their velocity constant? I would say no, it's not. When things fall, not only are they changing where they are and therefore velocitizing, but I would argue that their velocity is also changing, i.e., when things fall, they don't just have velocity. I would argue that they also have or exhibit or demonstrate acceleration. And we're learning about acceleration right now, so this is relevant, right? Now, why do I know that objects are accelerating? Well, for one thing, if I really want to be straightforward about it, I know that objects are accelerating. Like, we know they're velocitizing. Obviously, they're moving. But how do I know that they're changing the way they move? Well, one thing is, if I let something go, like if I'm holding something right here, I'm holding it at rest. Its velocity instantaneously right now is 0. If I let it go, it starts to fall. Within a moment of time, it's all of a sudden, it's very soon not going 0 anymore. It had 0 velocity, and now it has some other non-zero velocity. So it changes velocity. If it falls at all from rest, it's gaining velocity from 0 to some other number. So it's accelerating, right? Otherwise it would just hover. It would, if falling objects maintained constant velocity, then they would never start to fall, is what I'm saying. So certainly objects that fall accelerate. But if you don't like that, if you think that's a little bit cheesy or too simplistic, then I would invite you to think about lab 3. The first thing that lab 3 was meant to show us all, or demonstrate, or confirm, is that, right? If you remember lab 3, and apparently you've already done it, right, which is good, and I guess you've already handed in, which is good. Congratulations. But in lab 3, you made this. The first thing you did was you made a string, and you made sort of a control. You made a string. You put a bunch of bolts. I mean, tell me if I'm wrong, but you put a bunch of bolts on the string, and the bolts you arranged at equal space intervals, and you drop the string, and then the bolts hit the ground in non-equal time intervals, right? You space them out equally in space, but then they fall in like an ascending rhythm in time, like you hear da, 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 right? So in other words, it took the bolts less and less time to cover the same spatial intervals. So the bolts on the top, by the time they got to the bottom, were going faster, evidently, than the bolts at the bottom. So the first thing, just on a non-numerical, just on a qualitative level, the first purpose of that lab, in a way, was just to confirm, like, okay, when things fall, they don't just move, they don't just have velocity, they have acceleration. They're gaining velocity. That's the first thing in the lab. But now, where the lab gets funky, where the lab gets sort of challenging, and where you might have done a bunch of stuff and might have even have gotten it right and might have even have written it up, but maybe not been totally sure what you were doing or why. Let me tell you now, the next level in the lab was when you were supposed to be creating a string that actually did allow the bolts to fall in equal time intervals. And that took some thought and work on your part. It did not assume or require that you had any particular equations. Some people might have tried to use equations, but they didn't need to, and they weren't even really supposed to. You could have thought it through logically, or you could have done a bunch of trial and error for these strings. But here, I'm going to add a page to this now. Okay, just to remind you, and I know you did it. Like in principle, you know the answers that are coming. But what I'm trying to do here is show you what the answers to lab 3 actually mean for us here in physics class. Okay, so bear with me. In lab, and again, as always, please stop me if like I'm talking about something that did not actually happen, or if you're like, wait, what is he even? I don't even know what he. Right? I'm assuming that what I'm saying is familiar from lab 3, even if it was a couple weeks ago, and I'm now trying to put it into a context. So what I'm saying is you had this string and you had bolts on it. And what you first find out in the control is that if the bolts are equally spaced and you drop the string, then they don't land in equal times. The higher up bolts land closer together in time than the lower down bolts do, i.e., the higher and higher bolts are falling faster and faster by the time they get to the bottom. In other words, things are speeding up while they fall. That's what the control string demonstrates. But then the challenge was, okay, if that's true, can we compensate for this effect somehow? Can we take this effect into account and put bolts on a string that do, in fact, land in equal time intervals, like in a steady rhythm, right? That was our goal in lab 3. So I think what most people, if they're paying attention at all to the control, if they see what's going on qualitatively, if you see the big picture, I think many of you, I believe, realized pretty early on that, okay, as if we're going to arrange these bolts on the string, we better make the higher bolts farther apart. We better make these bolts like farther and farther apart. So when we drop the string, like the bigger spaces are covered in same amounts of time, and we'll get a steady rhythm. Like we better compensate for the acceleration. And if you thought anything like that, you're totally right. And you totally get it so far. And that's great, right? But then the question why it became a lab, or why this becomes sort of interesting, is, okay, but exactly like what numbers should we, like where, okay, farther apart, but how much farther apart? If we were going to like actually pick positions to put the bolts, and we put numbers to those positions, is there a pattern to those numbers? What pattern should we try? And there's an answer. I mean, there's one type of answer that works and one type of answer that doesn't work. Well, many types of answers that don't work. And to be sure, this is a sort of, it's meant to be sort of a fun, I don't know, fun, but it's meant to be like a not crazily high-tech lab. So it's not a super precise lab. It's kind of an approximate lab. But what I want to explain right now, I'm just looking at the time, is why just because you say that you want the bolts to get farther and farther apart as you get higher and higher in the string, just saying that does not answer the question of exactly how far apart they should get. Like some simple patterns seem very simple and reasonable and smart, but don't work. And others maybe seem less reasonable or less smart and do work. Let me show you what I mean. Oh, sorry. Okay. So I want to be clear about this. I'm showing you something that doesn't work because I want to make. Wait, do I want to show you what doesn't work first? Or... Yeah. This is a string this is an example of a string, and these could be centimeters or inches, or these could be centimeters, inches, feet, or they could be, these are just, these are It doesn't, it could be centimeters, inches, feet, or it could be each block is some, I'll even say unit. They're just units of length, like each, whatever the first unit is. Like if this is 0, from 0 to 1 is the first unit. It could be 1 centimeter, it could be 1 inch, it could be 2.7 centimeters. But then from then on in, all these numbers are multiples of whatever that first unit is, okay? This string seems reasonable. I mean, it seems honestly, this is the string that I would build if I were doing this lab for the first time. Okay, I'm not making fun of anybody at all. This is a totally reasonable thing to think, but I'm trying to make a point here. If I knew that I've got to put the bolts farther and farther and farther as I get higher and higher in the string, I would try to think of the simplest way I could make the bolts farther and farther and farther apart. And I would try it out. And one of the simplest things I could imagine is, okay, let me just keep doubling the length, right? I would put the first at 0, at the bottom edge of the string. And then the next bolt, like 1 unit away from that, an inch, a centimeter, a yavrobam, a cubit, whatever. And then I put the next one twice as high as that. And the next one 4, the next one 8. Like it's a very simple, straightforward pattern that seems totally reasonable. And the lengths the distances are getting bigger and bigger, and they're getting bigger in a predictable pattern. That seems totally reasonable. But let me show you why that would not work. Or, well, first of all, if you try it, hopefully you saw in the lab that it didn't work. But let me show you why that is. I'll even go a little higher just to make. Okay. Look what's happening. The very top bolt in this pattern, the bolt's at 16, it has to fall 16 meters, right, in a certain amount of time. The one underneath it falls 8 meters. So the one on top is being asked to fall 8 meters farther per unit time than the one below it, right? So if these were to fall in equal time intervals, let's say we're trying to plan it so that each bolt hits the ground every second, like some steady time interval. That would mean that the top interval, the top bolt is going 8 meters per second, 8 units per second faster than the one below it, right? And the one below that is going 4 units per second faster than the one below that. And the one below that is going 2 faster than the one below that. Okay, that seems reasonable. Like we're asking the top ones to go faster than the ones below them. That sounds reasonable so far. But then if we look, okay, how much speed is being gained every second? Well, so it looks like if you start all the way at the bottom, right? At first you're gaining 1 unit per second of speed. Then after that, you're gaining 2 units per second of speed. Then after that, you're gaining 4 meters per second of speed, right? So you're gaining speed every second. That's called an acceleration. That's fine. But look at the differences between those numbers. The reason I went another row and made brackets, like 2 is 1 unit faster than 1. 4 is 2 units faster than 2. 8 is 2 units faster than 4. In other words, it's the same pattern again, right? So in other words, and like it's the same pattern again. So I could keep seeing that pattern. I'm saying that if you double, what I'm saying is I could keep drawing these brackets and I could keep finding these differences as many times as I want to the right. The pattern of these brackets goes on forever. The top bolt is going faster than the bolt below it by a certain amount. And that amount is bigger than the amount at which the next bolt is going faster than the next bolt. In other words, I'm having a hard time articulating this. What I'm saying is that there's an increase in speed from one bolt to the next, but there seems to be an increase in that increase. And there seems to be an increase in that increase in that increase. And there seems to be an increase in an increase in other words, no matter how many numbers, if I make the string long enough and I start going to the right to see, okay, how much faster is the one going? If I start looking for, are we eventually gaining the same amount each time? Like we might not be gaining the same number of centimeters per each time, but are we gaining the same amount of centimeters per second each time? Like if I look to the right, no, because the numbers are going 1, 2, 4, 8. So then I'm like, all right, are those numbers always increasing by the same amount? So I draw another set of brackets to the right to the third, and I'm like, nope, those numbers are going 1, 2, 4, 8. And then I draw, I'm like, what's the difference between 1, 2, 4, and 8? Well, the difference is 1, 2, 4, 8. I could keep drawing those brackets forever, all the way to the right. And if that string worked, what I'm trying to say here kind of badly, what I'm trying to say here, so bear with me, if I just lost you in the last 5 minutes, I'll regroup now. I'll say this a different way. Come back to planet Earth with me. What I'm trying to say is, here's what I'm trying to say is, if this string worked, we'd have infinite changes. We'd have changes in position, changes in velocity, changes in acceleration, changes in jerk. We'd have a first derivative, we'd have a second derivative, we'd have a third derivative, we'd have on and on forever if this string worked. Because if you think about it, you can sketch out the brackets as many times as you want. You could look at as many numbers as you want, but there's always going to be a difference between the differences. They never taper off. I'm just showing 3 sets of brackets to show you that example, and I'm not doing it very clearly, but the amount by which these numbers are growing is growing, and the amount by which the growth numbers are growing is growing, and the amount by which the growth numbers are growing is growing. If this string worked, that would mean that when things fall, they get faster, and they get faster in the way that they get faster, and they get faster in the way that they get faster. That could all be possible, but this string didn't work. If you tried it, you'll know this string, they did not fall in like a string as simple as that. Double, 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 double. The things fall in equal time, the things don't fall in equal time intervals. So this is not the way that gravity works. What you might have known, and now maybe what I'm about to say will be a little bit clearer to everybody. What you might have discovered in the lab, or might have seen, or you might have talked about with your lab instructor, or you might have written up in your report is what does work, the string that does work sorry, I didn't, it's correct, but I just didn't draw it. This string, where your units could be anything, your units could be centimeters, they could be inches, or they could be some random thing like that first unit, that first bolt could be at 5.3 centimeters. but then, or something random like that. But then as long as the next bolt is at 4 times 5.3 centimeters, and as long as the next bolt after that is at 9 times 4.3 centimeters or whatever, and this one's at 16. In other words, as long as what you may have found or you may have learned or you may be realizing is that if your bolts are at the perfect squares, now this is also a pattern, right? This is also a pattern of numbers that are increasing. Like these numbers are increasing 1, 2, 4, 8. That's a pattern. That's a good pattern. But this is a pattern of increasing numbers that's very different. And this is the one that actually works. Now, this is the one where the numbers are in the perfect squares or in integer multiples of the perfect squares. And this is the one that actually works. Not coincidentally, you might remember that acceleration is measured in meters per second squared. And you might remember that the equation that we derived at the end of last class, last Wednesday, was that x equals 1/2 at squared plus v naught t, right? There's something about the squares that lends itself to acceleration. A square is a change in a change, but just that. Let me show you what I mean. And again, if you lost me 2 minutes ago, first of all, that's not your fault. I think I got very confusing 2 minutes ago, but get back with me. Like, it's not your fault. I hear you. But I think what I was just trying to say a minute ago about why something doesn't work will be clearer to you now if you see why what I mean when I say that this one does work. Look at the gaps here. Like between 1 and 4, the gap is 3, right? Like the bolt down here falls 1 unit in a second. The bolt above it falls 4 units in a second, right? So it falls like 3 units per second faster than the one below it, right? And the one here, the gap between 4 and 9, that bolt falls 5 units per second faster than the one below it, right? And the gap between 16 and 9 is 7. I'm just doing the exact same thing I did with the other string. I'm just looking at the gaps, right? Oops, sorry. I'm looking at the changes. I'm looking at how much farther each one goes per second. But now look at this. If I do this again, the gap between 5 and 3 is 2. The gap between 7 and 5 is 2. The gap, if I went up even higher to like 25 up here, well, I can't. Well, if I went up to 25, 25 minus 9 is 25 minus 16 is 9. The gap between 9 and 7 is 2. When I say gaps, what do I mean? I mean the differences. I'm literally just subtracting the numbers. When I say gaps, I'm just subtracting 2 numbers that are next to each other. And when I do that, I'm looking at change. I'm looking at how much faster a bolt above goes compared to a bolt below. And here's the fundament. And I think everybody in the lab understood at some level, if we want these bolts to go faster and faster, we got to put or if we believe that the bolts are going faster and faster, we got to take bolts that are high up and ask them to go a lot farther distance in each unit of time than the ones below. So I think everybody like understood the bolts should be farther and farther as they go. But I'm saying between these 2 simple examples of increasing patterns, there's a big distinction between these 2 patterns. In this one, the top bolt is going faster than the bolt below it by an amount that is more. They're not just increasing speed here, they're increasing the way they increase speed. And they're increasing the way they increase because no matter how many brackets out I go, I'm never getting the same list of numbers with the brackets in this example. Again, there's something very messy and confusing about this page. I recognize that, but partly it's messy and confusing because I'm trying to say this one doesn't work. There's always gaps between the gaps. There's always an increase in the increase, no matter how many we subtract. There's always something to subtract. But here, like, the gaps between the perfect squares are the odd numbers, 3, 5, 7, 9. And the gaps between the odd numbers are just 2, 2, 2, 2, 2. In other words, there's a change. So what I'm saying is, what I'm really literally saying is this. And then I'll stop. Hopefully I'm saying if where you put the bolts is called position, right? Like X. And if how far apart the bolts are, how far one gets per unit time, the next row, the gaps is velocity, then this row is acceleration, right? The first red row is change in position. The next red row is change in that. And with this bolt, if you put the bolts at perfect squares, you notice there's no change in the acceleration. That's what I'm trying to say. And I don't care that the number is 2. It doesn't matter that the number is 2. The fact that it is a number that's not changing is what shows, like, the fact that this bolt, that this string works, this string works. This string does not work. This string does not work, because if this string did work, that would mean, or let me put it the other way, the fact that this string does not work means that there's not a change in acceleration when things fall freely to Earth. The fact that this string works means when things fall to Earth, they do change their position. Therefore, there's a velocity. And they do change their velocity. They do go faster and faster. Therefore, there's an acceleration. But they don't get faster and faster by a faster and faster amount. They change their velocity, but they don't change their acceleration. The fact that this string work shows, this is the point of lab 3, and then I will stop. But I'm trying to say that in the end of the day, lab 3 is not even trying to prove numbers or make you memorize numbers or anything like that. It's trying to show you that free fall is an example of a phenomenon where there is a change in velocity, but there's no change in the change. That there is an acceleration, but the acceleration is constant. This is trying to show that when something falls, it falls at a constant rate of acceleration. Therefore, okay, and that's a conclusion of lab 3. The big conclusion of lab 3 is that free fall is an example of constant acceleration from now on. So it's an example where A equals A naught. That means when things free fall, when they free fall down, or even when they free fall up or over, when something is just like in midair and subjected to nothing but gravity, we can assume from now on, I mean, we can believe from now on that it is accelerating toward Earth at a rate that is approximately constant. Now, what is that rate? Well, it totally depends what units you measure in, right? Which is why you get different numbers for different strings. If you want to measure in feet per second squared, the number is 32 feet per second squared. If you want to measure in miles per hour per second, it's 22 miles per hour per second. If it turns out that you want to measure that number in meters per second squared, then the number is approximately 9.81 meters per second squared. And how do I know that? Some of you might have gotten to the stage in the lab where you could actually determine this number. Some of you might not have. But how we would determine this number, once you do all the string stuff, once you established, if you made a string where the bolts were at the perfect squares, as in meters per second squared, as in x equals 1/2 AT squared, as in second degree polynomial, as in an algebraic function that has 2 derivatives, but not 3, right? Once, which is really what we're saying, then you realize, okay, the way to describe gravity is a constant second derivative. And therefore, i.e. that A equals A naught. Therefore, what you're saying really by the end of lab 3, and you may not have understood this while you were doing it. I get that. That's why we're talking about it now. But the purpose of doing lab 3 was that by the end, if the perfect square string works, what that's actually telling us, if we follow the reasoning, is that free fall produces a constant acceleration, an A equals A naught situation. Therefore, any of the equations that we've established thus far work and apply, such as x equals 1/2 AT squared plus V naught T. Therefore, once you do lab 3, if you finished it early or whatever, you could just take an object, drop it a known measured distance, measure the amount of time it takes to follow that distance, and just plug into x equals 1/2 AT squared, and you'll solve for A, and you'll find, I mean, some of you may have done that, some of you may not have, but the point is it's not possible to do, or it's not fair to do, unless you believe that there's a constant A. But the strings show that there's a constant A. They show that that equation is legit. From that, we determine that the approximately constant acceleration due to gravity in free fall is approximately 9.81 meters per second squared. I keep saying approximate because we're rounding. It's actually an infinite set of non-repeating digits. So we chop off the digits at number 2 if we want. We call it 9.81, squiggle, approximately. But if we want to chop them off even more, often physicists, not just students, all physicists, especially if they're in a homework problem, a theoretical problem, or an exam or something, they'll round that whole thing to 10. And we'll say that the acceleration due to gravity, the constant acceleration in free fall, from here on in, is approximately 10 meters per second squared. That means if you drop something by the end of the first second, it's going 10 meters per second. By the end of the second second, it's going 20 meters per second. By the end of the third second, it's going 30 meters per second of velocities. How far does it fall? That we have to be careful about, and that we have to use the new equations for. Like it takes a little thought to figure out how far it falls. But what its velocities will do is just follow that pattern of increasing by 10 at every second. Do we call that a positive or a negative? We just call it a number. And whether we make it positive or negative depends on the coordinate system that you've chosen, whether you've chosen to assign down as positive or down as negative. That's a choice, just like you were supposed to make in the very first problem of homework 4, when the woman flies from Berlin to Rome, and you have to make a little diagram, and you're supposed to, in that diagram, choose your coordinate system and decide whether south is called negative or positive. And then based on your choice, then you get answers for displacement and average velocity that either do or do not have a negative sign in them. It's Galileo's principle. It's up to the laws of physics work the same in all inertial reference frames and all coordinate systems. So we always have to assign our coordinate system first to decide on negatives or positives. But once we make that decision, then it applies. So I'm saying, I don't know if this is, don't memorize whether this is a negative number or a positive number. It can be either one. But from here on in, free fall is an example of constant acceleration. The value of that constant acceleration during free fall is approximately 10 meters per second squared. That's a big takeaway. Like you can, that's not an equation, that's a value. But if you're like memorizing things in this class or keeping track of like pieces of knowledge in this class, definitely add that to your sheet or whatever. That's something you want to know. It's always given on exams, but we do assume that that is a piece of knowledge from here on in. That free fall is an example of constant acceleration. The rate of acceleration is 10 meters per second squared. Now that applies to free fall. There's lots of situations where things accelerate constantly and they might have a different value because they might be on a ramp or something like that. They might not be free falling, but this is the free fall value. Now that's supposed to be the takeaway of lab 3, or a big takeaway. It's also very much applies to lab 4. We'll address that soon. But for now, with 12 minutes left, I'm going to do an example. With 12 minutes left, I have to do 2 quick things. Actually, I'm going to do them a little bit quickly. I want to give you one more equation that we can use in constant acceleration situations. This is the point of the I'm going to do this a little bit quickly. The very last problem on homework 5, what seemed like raw algebra. Sorry, we did that. Sorry. Okay, the very last problem of homework 5 looks like raw algebra. The purpose of it was to establish some raw algebra to make sure you are okay with algebra so that we could take equations we already have and derive a new equation. I'm going to say this quickly. It's in your note. I'm going to just point out what this is in your notes, and then you'll have the notes. Sometimes, like whenever you're given a situation where you know the time that something is moving, and you know the constant rate of acceleration that it's moving, and you know the initial velocity, then you use this equation x equals 1/2 at squared that we established last Wednesday, and we're going to keep practicing. We're going to practice it in a minute. But what if you ever given a situation where you're not given the time and you're not solving for the time? What if you're just given like the acceleration rate, the initial velocity, maybe the final velocity in the initial position, and you just want to know? So I'm saying, what if you're solving for displacement, but what if we, in other words, I'm going to turn the page now. What if we don't know t and we're not solving for t? then what I do here, I'm just going to summarize this quickly. Here it is in the notes. I'm going to summarize quickly. What I do here is I take the equations that we already have that are true for constant acceleration, and I algebraically put them together. I assume, in other words, that we're solving for x, but that we don't know t and we don't care about t. In other words, it's like two equations, two unknowns, two simultaneous equations. So here in the notes, I just take equations that have t's in them and I put them together. I substitute one into the other. That's what's happening right here. You don't have to scramble to take, you can take these notes down, but obviously I'm going to upload this PDF. All I'm doing here is doing algebra to take two equations that we already have, put them together. I put them together. Okay, I get a difference of two perfect squares. It's just a bunch of algebra. It's here in the notes, but I algebraically take two equations that we already have and I put them together to get rid of the t's. Like I rewrite them each in terms of t and I substitute one in the other so that I end up with this big equation that's circled at the bottom of page 9 here. And it is the same one that was on the front page of the whole day today. So this is another equation to add to your list. It's the final equation for constant acceleration motion. It's the purpose of this equation, and it's double equal sign. It's only true when you have a value for a. It's not the most exciting equation in the world, and it doesn't have new knowledge in it or anything like that. It's just a shortcut or a trick that comes up a lot whenever you don't know time and you're not solving for time, when time just is not there for you and you have all the other information, you use this equation. Okay, and we got it by just taking our old information and algebraically putting them together once and for all. That's what this is. I mean, I do want you to know it. Again, we always give the equations on tests anyway, so it's not about memorizing, but I want you to be aware that you're responsible for this. And whenever you get a problem where you're not being asked for the time and you're not given the time, don't forget to consider this one. Okay, it's the last of our, I think it's equation number 8, maybe, or 9. It's the last of our constant acceleration equations. Okay, and again, if you want the details, it's all in the notes here that will be in your Google Classroom. But now I want, with 8 minutes left and with 3 pages, what I want to do is turn to the homework that I just uploaded for, like, again, so that was the purpose of the very last question, the very last problem of homework 5. So we've now actually gone over every single problem of every homework sheet, believe it or not. From here on in, we're not necessarily going to go over every single problem of every homework sheet. We're not going to go over all the problems. You'll get solutions, but we're not going to go over all the problems of this next big homework sheet. But right now, I'm going to do one of them for you right now. If the next homework that just got uploaded, that's due next week, that's homework 6, it's called Big Old Duck. Problem 1 is sort of an exercise that you can go, it's like a chart you fill out, you do, it's not so bad, it's practice. I'm skipping that for right now. But number 2, I'm going to do for you right now with 7 minutes left, because I want you to see some of this in action. So this is problem number 2 on the new homework. You're not expected to have done this yet. I just assigned it. I'm just doing it for you. Okay. And you still have to turn it in, but you can use this and just put in your own words. So here's problem number 2 on homework 6. What we're given, and we have 7 minutes left. And as always, I'll hang out right after you have any questions or anything like that, but you go when you have to go. So problem number 2, homework 6, we have a slide. We have a slide. We have an object that's starts from rest, a baseball that's rolling down the slide. It's rolling from rest, we're told that, and it rolls at a constant acceleration. I'm going to call the initial position where it starts, I'm going to call that 0 because I can Galileo, like I'm labeling, like I'm calling the first place 0. I'm saying, okay, the acceleration is a constant. This is a slide. There is a constant acceleration, I'm told. I'm not assuming for this problem that it's 10 meters per second squared or 9.8, because this thing is not free falling. It's not falling straight down. It's rolling on a slide. So it's going to be some number that I would expect to be bigger than 0. And I would frankly expect to be less than 9.8, but I wouldn't expect it to be as high as 9.8. I don't know what it is yet. Maybe we're going to solve for it. I just know that it's constant. So we're given also, so this is my diagram. This is my step 1 DFP. I'm labeling everything. I'm labeling that the whole displacement is 6 feet. Like I'm told, the whole time is 2 seconds, I'm told. And also please notice, as really would have been helpful if we had all done in that Berlin-Rome problem, the first one on the homework 4, like I'm also putting arrows to say what's positive and what's negative. I'm labeling my coordinate system. It seems simple and straightforward, but it's like super important. And notice I'm making this choice. I'm labeling down as positive because first of all, I'm allowed to do that. Galileo says the laws of physics apply in any coordinate system, any unaccelerated coordinate system. I'm choosing to orient my coordinate system so that down is positive. And you might say, well, okay, maybe you're allowed, but that's like weird. Why would you, I mean, what? Because since I'm allowed to make whatever decisions I want within reason, and I want to make my life as convenient as possible, this object only ever goes down. It never changes direction and goes up. It only ever goes down. So I'm going to call down positive so I can minimize the number of negative. I don't want negative signs unless I need them to distinguish from positive. Negatives are definitely harder for everybody, including real physicists. So real physicists are smart enough to know that they're not that smart and they'd rather not deal with negative signs if they don't have to. So I'm calling down positive. Do you have to do that? No, but you have to make a choice. You have to tell me what your choice is. I'm choosing to call down positive. Now with that, so that's my DFP, step 1, right? Step 2, the question, and so those are the givens. The question is, at what time does this object achieve an instantaneous velocity of 3? That's like an unusual new sort of question. I'm not saying it's hard, but it's kind of an unusual question. So I write down my GDPs here. This is step 3. I probably should have labeled it. Average velocity is displacement over time. Average acceleration is defined to be change in velocity over time. Those two are definitions. They're definitely true and seem pretty topical. So I would definitely get points for those, even if I don't know how to use, even if I don't know where I'm going yet or how I'm going to use them. I'm writing down things that I know are true. And then I know that A is A naught. So I know that this thing is true as well. I know that average velocity is the average of velocities in this situation because I was told that the acceleration is constant. I don't know what it is, but I know it's constant. So I wrote down my GDPs, my knowns. Now, I start solving. I'm doing step 4, PAW. V bar equals 2 feet over 2 seconds. Okay, so V bar equals 3 feet per second. Now, what is that? That is not my answer necessarily. In fact, it's definitely not my answer. What that is my average velocity for this whole thing. But what it's asking me is, when is my velocity 3? And I just got the number 3 as my average velocity. Some people might think, oh, well, okay, so we just got 3 is the average velocity, and the whole thing it takes 2 seconds to go. So some people might think, okay, so 3 feet per second. So he arrives at 3 feet per second at the end of the ramp at the bottom. You might think, if you're not careful with GDPs and stuff, you might think, oh, all right, so he achieves a speed of 3. So at the end of 2 seconds, but no, 3 is my average, right? 3 is the average velocity. So since acceleration is constant, that means the average velocity occurs in the middle of the time, right? Really, what I'm showing down here at the bottom, however you want to say it, that recent equation of ours is telling us that this average velocity is what I achieve as my instantaneous velocity right at the middle instant. I start at 0, I build up speed, and within 1 second, I get up to 3 feet per second. And then in the next second, as I keep traveling down to get to the end of the whole thing, I'll get all the way up to a maximum speed of 6 feet per second, right? If you're following the reasoning of acceleration, this thing builds speed continuously from 0 to 6. So the answer to the question, when does it achieve an instantaneous velocity of 3, is right in the middle at t equals 1 second. I'm not saying, you might have gotten that right. You might have even seen it in your head. Well, I mean, you just got to, you might get that right in your head, but I'm just trying to establish how average and instantaneous relate to each other for constant acceleration. It achieves the average velocity right in the middle. But then we have 1 minute, we have 1 page. The real interesting question here is question B, where it asks, how far has it gotten in that 1 second? How far has it gotten by the middle of the time? And what I'm here to say with 50 seconds left is it does not achieve the middle of the distance. In half the time, this thing does not travel half the distance. Why? Because it's speeding up. It's not going at a constant velocity. It doesn't do the same amount of distance for every time. if you incorporate the acceleration rate here of 3 meters per second every second, if you note it's gaining 3 meters per second every second, then just like the bicycle problem on the last sheet, it'll travel only 1.5 meters in that first second, because on average in that first second, it's only going 1.5 meters per second, right? It's going slow on average. It takes the entire first second to reach a speed of 3, but it started at a speed of 0. So on average, it's only going 1.5 meters per second. So in that first second, in the first half of the time, and I know the time is 4:20, so I'm about to end my sentence and my page and my class. In the first half of this journey's time, this object only achieves 1/4 of the total distance. In half the time, it achieves 1/4 of the distance. 1/2 squared is 1/4. It's all about squareds here once acceleration's involved. In the first second, it achieves 1.5 meters, and in the next seconds, it does all the remaining 7.5 meters, because it's building up speed as it goes. Constant rate of acceleration is a changing rate of velocity. That's it. I'm done. Thank you so much for being so attentive and engaged. And more is coming. If you want to hang out for a second and ask a question or whatever, or copy a page, that's fine. But I'll see. Yes, have a good day, Anthony and Montserrat and Katya and everybody. Thank you. But I'm here just in case there's questions. Thank you. Awesome. And I'll turn off the recording. Have a good day, Brianna. Awesome. Awesome. I'm changing everything.
Professor, can you go back to the page you had before this one?
I would love to do that. I love when people ask me that. It's like shows that you're totally, yes. In fact, who is that? Kay? Who just asked me? Is that Kay? Sorry.
Yeah.
Okay. Yes. Yes. This page right here.
Yes.
Okay. Awesome. Oh, and are we still? Sorry, I'll stop the recording. But good job. We're okay to the world.